All right, welcome back, everyone. I hope you had a nice break. I hope you're not all watching this the night before the quiz, but I'm sure some of you are. Good luck. So, in the last portion of this lecture, we talked about three types of chemical bonds that are important for life: covalent, ionic, and van der Waals interactions. I wanted to take a moment and have a special lecture specifically on hydrogen bonds because these are bonds that if you didn't have a strong um, didn't have a strong biology course in high school, you maybe didn't spend much time to think about. But really, they're the basis of a lot of um, the molecular mechanisms we're going to talk about in this class. So you should spend some time on this lecture. It's really important you understand what a hydrogen bond is. And hydrogen bonds are the result of molecules that have polar covalent bonds in them. And so if you're still confused about polar and non-polar covalent bonds, talk to your UTA, read the book. I'll put some links to, say, a Khan Academy YouTube videos. I'm really not offended if you guys go on YouTube to find a lecture of someone who's doing it better than me. Yeah, I have no pride. I don't care where you get your information from. I hope I'm helpful. But at the end of the year, we just want to make sure you have a firm grasp on modern biology. And I really, I'm not offended if you get help elsewhere. So let's talk about hydrogen bonds. What is a hydrogen bond? The most common type of hydrogen bond in biology is the hydrogen bond between water. So let me move my mug here down there. Not that you guys want to look at it anyway, but so um, let's look at a water molecule again. So water is a highly polar molecule. It has two polar covalent bonds in it. And that's because, if you remember, oxygen is more electronegative than hydrogen. That means that in the covalent bond between the oxygen and the hydrogen, the electrons in this bond are more attracted to the oxygen than they are to the hydrogen. And as a result, there's more of a negative charge associated with the oxygen molecule because the electrons are negative. And since the electrons are pushed towards or pulled towards the oxygen atom, the hydrogen atom, which has a proton in it, has a slight positive charge. And if we look at how this molecule is charged, there's a slight positive charge associated with each of those hydrogen atoms in water. And there's a slight negative charge specifically associated with the unpaired electrons on the oxygen in this molecule. Think of this as a magnet. My daughter loves toy trains. And I'm sure you guys had toy trains maybe as a kid too, where there's a magnet on either end, and you push them together. And if a negative pole of one magnet is interacting with the positive pole of the other magnet, they pull each other together, right? There's attraction between them. And the opposite is true. If you try and take the positive pole of a magnet and shove it against the positive pole of another magnet, they repel each other. Opposites attract, which is true in life in general. And so the small magnet that is with water will form bonds with other water molecules. So let's look at how that works out. So because each water molecule is sort of like a mini magnet, it'll form a weak bond with another water molecule. So when it's in its liquid form, the positive regions associated with the hydrogen of one water molecule will form a weak bond with the negative regions of another water molecule. And because there are these four dipoles in a water molecule, two positive charges associated with each hydrogen atom, two negative charges associated with the unpaired or with the paired with the unpaired electron pairs, the pairs of electrons that aren't bound to anything in the oxygen. One water molecule will form four hydrogen bonds with other water molecules. These are essentially like magnetic connections, right? A negative attracting a positive. Now, these are weak bonds. So the strength of a hydrogen bond is about 1/20th or 5% of the strength of a covalent bond. And these bonds readily break, right? You can shove your hand into a bucket of water. So these bonds break and reform and break and reform, but they're there. And when there's a lot of them, they can hold a lot of sway over the media that they're taking place in. And these types of bonds are essential for life. Um, and they impart a couple key qualities on water. So let's start by talking about what do these bonds do in terms of water. Actually, let's not. Let's take a pause here. Okay, so these bonds impart certain qualities upon water. And really, they serve as the foundation of life on Earth. So let's examine how hydrogen bonds and water itself are essential for life. So water, because of its ability to form hydrogen bonds, has 4 emergent properties. And these are the 4 properties of water you should know. And when I say that, I'm saying that because you should know that for the exam. So we are an intro level course. I want to give you guys clues on how to study. And so when you see a PowerPoint slide like this, where there are bullet points numbered, you should know those bullet points. So in this case, I'm telling you there are 4 emergent properties of water that are present because of hydrogen bonds. It means that it would be very easy for me to write a test question that says something like, what are the 4 emergent properties of water that support life? All right. So let me move this. Nothing else, you can watch me move my face around. Okay, so those 4 properties are water expands upon freezing, it moderates temperature, it has cohesive behavior, and it exhibits versatility as a solvent. So let's look at each one of these. So the first one is water expands upon freezing. And if you look at the planet Earth, the whole planet is basically a ball of water with some land in it. And as seasons occur, surface water freezes into ice. And when it does so, the structure, the molecular structure of water changes. So if we look at liquid water is filled with water molecules moving around, forming hydrogen bonds and breaking hydrogen bonds. These are weak bonds. As the molecules move around, they break and reform and break and reform. There's no definitive structure, and the molecules can pack more closely together. But as the temperature lowers, these bonds are formalized. The molecules don't move around as much. And so in ice, each molecule is bound to 4 neighboring water molecules. If we go back 2 slides, it's what you see here, right? There are 4 different magnetic poles, electrical poles on a water molecule. Each one can form a hydrogen bond. In ice, that's what's happening. The molecules have slowed down, and you end up with static molecules, or more static molecules, where each molecule of water forms 4 hydrogen bonds. That doesn't happen in liquid water because those molecules are moving around. As a result, the molecules in liquid water can pack more tightly. And because of that, ice is less dense. There are fewer water molecules per unit of volume in ice than there are in water. And as a result, ice floats. And when it does that, it also insulates the water below. So you get less ice forming at the bottom. This is key for life, because if ice was more dense than water, ice would sink and the oceans would fill from the bottom up with ice, and we would have never had life on this planet. But because it flows, because it's one of those unusual substances where the solid form is less dense than the liquid form and it floats, we can have oceans covered in ice with life underneath. All right. The second key aspect of water is that it moderates temperature. And I don't know how many of you have lived in the desert. So I spent 6 years out west. after I got my PhD in biology, getting a PhD isn't enough to get you a job. You have to do another internship called a postdoctoral fellow. So we'll talk about this more later, but if you want to be a biology professor, you do 4 years of undergrad. I did 6 years of grad school and another 6 years of a fellowship. And that qualifies you to become a biology professor, in molecular biology at least. So I was out in the desert, and out in the desert, there's no water. Well, there's some in Salt Lake City because there's a Great Salt Lake, but in the desert, you have these massive temperature swings between 100 degrees during the day, and it'll drop down into the 40s or 50s at night. And that's because there's a lack of water out there. Water absorbs heat and releases heat. It has this incredible ability to modulate air temperature. And you can see that in Lake Michigan. So if you look at this graph, you look at the months on the x-axis here, temperature on the y-axis. Remember, we'll spend some time talking about graphs next week. If you look at air temperature in green here, you can see these wild swings in air temperature where it's really high in June and July and really low in January and December and November. But the water temperature doesn't fluctuate nearly as much. It takes a lot more energy to change the temperature of water. And the result is that the air over Lake Michigan is either warmer or colder than places elsewhere in the Midwest where there isn't as much water. Because it absorbs heat from air that's warmer and it releases heat into air that's cooler. And this is because of the specific heat of water. So water has a specific heat of 1 calorie per gram per degree Celsius. So that means it takes 1 calorie of energy to change the temperature of 1 gram of water by 1 degree Celsius. That's actually a decent amount of energy. And because of that, the areas around the oceans and Great Lakes don't experience as large of temperature fluctuations as places that don't have it. And if you're an organism that lives in the ocean, you don't experience nearly the temperature fluctuation that an organism that evolved later and lives on land does. All right. We'll come back to that. The third key property is water is cohesive. The hydrogen bonds hold the water together, and that allows water to move up against gravity. So for example, if you look at a plant, the key for photosynthesis is water. Those leaves have to have water in them. How does the water get there? Well, it gets absorbed from the ground. And so it has to move up against gravity to get to those leaves. And the only reason it can do that is because water is cohesive and it moves through these water channels in the plant called xylem. And it'll move up the trunk into the leaves. And that's because as the water moves up, these hydrogen bonds between the water molecules, known as cohesion, the clinging of a substance to itself, and adhesion to the sugars that line these xylem, cellulose, allow the water to get pulled up more easily. And so water can move against gravity in plants. Or if you've ever looked at water in a graduated cylinder, you see this meniscus as the water moves up the sides of the glass. That's adhesion of the water molecules to the glass, cohesion of the molecules themselves. Okay. And finally, water is the solvent of life. A lot of things dissolve in water. Anything that has polar covalent bonds in it, or ions, anything with a charge, can dissolve in water. And we're going to use the terms related to solutions quite a bit in this class. And to just define them, a solution is a liquid that is a completely homogeneous mixture of 2 or more substances. So think of salt water. Salt water is water and a number of different minerals in it. The solvent is a dissolving agent. So on Earth, that's often water. That's the most common solvent. The solutes was dissolved. So sodium chloride, for example, salt dissolves in water. And an aqueous solution is a solution in which water is dissolved. And for those of you who are interested in medical fields, and usually I ask people, the first day of class, I'll ask all of you to raise your hand if you want to go to medical school or dental school. Probably about 80% of you want to try and go to one of those want to go to one of those professional schools, and I'm confident in all of you. One of the things you'll encounter are saline solutions that you use to rehydrate patients. And so a saline solution is simply a low concentration of sodium chloride and probably some other minerals that it has a solute concentration similar to blood. And this is an example of how water is an excellent solvent because it can hold those salts in solution. All right. And we often talk about water as a solvent in terms of salt or sugar, right? We've all done those experiments in grade school where you dump table salt or sugar into water and watch it dissolve. But it's also, and that's shown here. So you can look here, how water molecules will interact with the chlorine and the sodium ions in table salt. And it'll break those ionic bonds because these ions are reforming hydrogen bonds with the water molecules. The same is true of glucose. Glucose is full of polar covalent bonds. Hydrogen's bound to oxygen, so a glucose molecule has partial positive and negative charges. All of these molecules easily interact with water. Glucose forms hydrogen bonds. Each one of these OHs and this oxygen will form a hydrogen bond with water. So water can surround these molecules and dissolve them, allow them to remain suspended in water. But it's not just these small molecules that dissolve in water. So very large molecules also dissolve in water. So for example, proteins, like the spike protein on viruses, those very big molecules will be surrounded by water molecules. And all of these water molecules form hydrogen bonds with those larger proteins and allow them to be suspended in water. So for example, this is a lysozyme molecule here, is a type of protein. And the surface of this molecule has lots of polar covalent bonds on it. And so the water will surround it and suspend it in the water itself. Substances that can dissolve in water are known as hydrophilic. Hydrophilic substances have an affinity for water. And these are molecules like sodium chloride and glucose, proteins, not all proteins, but a lot of proteins. All of those things that you can suspend in water. There are also substances that won't suspend in water. These are substances that don't form hydrogen bonds with water. And a good example of this is bacon grease. If you've ever had bacon in the morning or some other meat that makes it's very fatty and it leaves a film in the pan, those molecules, those fat molecules in grease, are full of non-polar covalent bonds. So they're not charged, they don't interact with water, and those molecules don't dissolve in water because they won't form hydrogen bonds with the water molecules. And so this is a clever cartoon that Dr. Bergsten, I stole from her as well. It says, help, I'm dissolving. It says, but bears are insoluble. And then this bear says, it's not easy for you to say you're not polar. Anyway, all right, so, and it's not just proteins. DNA is, the structure of DNA is dependent on water. It's the interactions between water molecules and DNA that gives it the structure that you guys are familiar with probably from high school. And in fact, Rosalind Franklin is really the first person to demonstrate experimentally what the structure of DNA is. We often talk about Watson and Crick, but it was really this woman. She's a fantastic biochemist, world class, absolutely exceptional. Should have won the Nobel Prize, but died before they awarded the prize. But some of the bastards in Sweden are too sexist anyway. They would have never given it to her probably. But she was amazing, super talented. And the reason she was able to see the structure of DNA, to elucidate the structure of DNA, was because she could make crystals of DNA with water in them. And no one else was able to. And water is so integral to the structure of DNA that, it doesn't form its proper three-dimensional helix that's found in cells without water. All right, so let's end here by having two quick exercises. I'm going to show you two molecules, and I'm going to ask you, is it hydrophilic or hydrophobic? So let's start here. So what do you guys think? Well, if we look at this molecule, you can see that there are a number of polar covalent bonds in this molecule. The OH bonds here, the bond holding the hydrogen to the oxygen, this is a polar covalent bond, as is carbon to oxygen. Oxygen will pull on the electrons both from carbon and from hydrogen. Because of that, there's a lot of partial positive and negative charges in this molecule, and those partial charges will interact to form hydrogen bonds with water. This is hydrophilic. It will dissolve in water. Okay, let's look at another one. This is palmitic acid. This is a fatty acid. All right, this is hydrophobic. If you look at this molecule, there are a couple polar covalent bonds in this molecule. One here, one here, one here. But the majority of this molecule is filled with non-polar covalent bonds. The hydrogen-carbon bond, these two atoms have similar electronegativity, and there's really not much of a charge on any of these carbons and hydrogens. It won't dissolve in water. This is a fatty acid, right? It's fat. It doesn't dissolve in water. Now, you might ask, well, if there are some polar covalent bonds in here, how do you determine if it's going to dissolve or not? This portion of the molecule will interact with water. But the key is, it's usually considered the ratio of nonpolar carbons to polar covalent bonds. So in this case, it's like, I don't know, 15 to 1. Anything more than 5 or 6 to 1, and I would call it a hydrophobic molecule. All right, so we'll end there. And don't worry, on an exam, if there's any question, I'll try and make it so it's not subtle, right? Okay, we'll end there, and we'll pick up with a lecture on pH, and that'll be the last lecture for today.